All right. So for this, we're going to go through some you know, beginning stuff with R, how to deal with for coding. And close this. So what I want to do then is I'll share screen here. Okay. This is the R Studio. This is for some code just been putting together for our project. This is like a test run. Um, and I can start posting some of this on our GitHub, so you don't have to like worry about memorizing this or anything. But if you've done R, at least like a quarter of R, some of this should look familiar. You don't need to do this, but just as a habit, I usually just include this at the beginning of my code. This just means like purge memory. I usually just like to put that at the beginning of whatever I'm running, just in case. So I'm not like carrying over any information from before. Everything else here, these are packages that I use to run stuff on to be able to carry out various parts of the analysis. So in this case, there's a couple of different packages I use. RGDAL is actually, it's a GDAL package for R. So there are things I use. I do like, this is a lot of geospatial stuff. RJava is the R package that allows you to talk to Java. And the reason why we have to talk to Java is because maximum entropy, so that species modeling technique, it's actually built in Java. And for whatever reason, nobody's written like an R version of it. So max ent is written in Java, and then you have to install this Java thing in R, and then you have to install this thing in R to talk to Java. It's wonderful. All right. Any of you who get around to installing and getting maxent to run on your machines, please let me know. There's some weird stuff about it. All right. The next one is called Dismo. So Dismo is like it's a species distribution modeling package that allows you things like random forest, maximum entropy, and so on. So it allows us to actually like make maps of like where we expect species to be. Roster is the package that allows you to deal with like rosters, like map rosters. And the last one is Parallel, which allows you to do a lot of things where you're actually telling your computer to run things in parallel if it can. So it speeds up calculations, because let's say if you have like 4 processors, it'll usually take 3 of them and then chop up what you're doing and then run things in parallel. So it speeds it up. All right. And there's plenty other packages. These are just the ones that I've ended up using so far. All right. Stop me, this is all really boring, but working directory, in this case, this is where my files happen to live on my computer for this project. And then I just say, okay, working directory is this path. And then I set the working directory. And this thing here, set seed. So a lot of the stuff we're going to end up doing, we're going to be like randomly taking data for things, for subsetting stuff, which is really useful. However, here's the trick. Because remember, we're trying to build code that where you can do things reproducibly. You want to generate random, or I guess it's really pseudo random numbers for things, but you want to do it in a way that it's reproducible. And what you can do is you can say set seed, and you specify a number in there. It doesn't really matter what the number is, as long as you just kind of always use it. Set seed means, I know you're going to use a random string of numbers to do stuff, but always use the same string of random numbers. So even though you'll do something that's random, when you rerun this code, you'll get the same results back. If you don't set seed, it'll be a new random string each time. So, and it doesn't matter what number you put in there. I just kind of usually put 1 or something. All right. So for this, and I think this is from Michelle, but this is a species input data. This is, we can export this from GBIF. So we run like that whole query on GBIF, and we say, okay, give us all the species observations within like, last 10 years or whatever that are within, I think it was like 30-meter resolution, that we have coordinates, that we know that down to species and that sort of thing. And what this does here, read table, means, okay, take your data, in this case it's a spreadsheet, read it into a data frame. which is a type of object. So we're doing read table, tell it what the header is. So the top row is the header. Tell that it's a tab delimited here. As is means like read in everything, don't change it, don't skip any lines. Fill equals true means if there happens to be a blank value in the spreadsheet, just put in an NA value in the data frame. And check names is false basically means don't take the first column and assume that those are row names. And the text encoding. So you can actually, this whole string here is just like a lot of stuff I use just to like make sure it's reading it incorrectly. So let's run this. I'm just going to run, you can just highlight everything there, click run. Okay, it's installing packages, blah, blah, blah. All right. There we go. Okay, so now when I click and I run this, my new read table, it's going to show up in the environment. It's going to be a data frame. Okay, so now when I input species input, I can click and open this. So I've got like 127,000 rows and 50 variables. What does all this stuff correspond to? Well, there's like some GBIF identifier, another identifier. This is like the within like whatever database of databases it's located. So it says observation.org, that's one. This is a different database. Remember, GBIF is like multiple databases. And then it gives you all this data like kingdom, phylum, down to species, for what kind of taxa we're looking for. Okay. And the next stuff, yeah. Then we have all this other stuff here. And we also have this taxon rank. So taxon rank is just telling you how, like, to what level do we know it? So in this case, if we know if this says species, it means we know the taxon resolved down to species. If it says genus, it means we only know it down to genus level. Scientific name, verbatim scientific name, and all right, and then basically, then there's a bunch of other information here. So we have locality. Okay, the current status, this is kind of redundant, but the current status means like we're only doing presence only data because we don't have reliable absence data. We just know if things were there. We don't know, there's no data that we're using that's like, oh, we try to look for it and it wasn't. Then we have the count data. And okay, a lot of this, and then we also have the decimal latitude, decimal longitude, which is like where stuff happened to be located, which is gonna be useful for us. Coordinate uncertainty in meters. This varies a lot, but I'm only, it should only be with up to 30. And okay, elevation. A lot of times they don't have elevation data, it's fine. Okay, event date, day, month, year. Yeah, human observation. Some of it's human, some of it's machine. Anyway, you kind of get an idea of like there's all this information that's stored in here. Not all of this we necessarily need to use for what we're doing. Okay. So now I just want to filter it. So I'm only keeping stuff we know down to species. So take note, it's 127,399. Let's see what happens when I run this. Okay, cool. That means, yeah. So it means some of these things we don't know down to species. I want to remove those. So I took off a few thousand there. And then I'm renaming decimal latitude, decimal longitude, just latitude, longitude, just so I remember it better. This command here, by the way, this will just rename variables. Okay. Now, here's this whole thing that we're doing. Okay, convert species location. By the way, comment your code. Please, 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 just get in that habit because you're not going to remember why you did stuff. So convert species location to a spatial data frame. We're assuming that we have a CRS of EPSG 4326. So our latitude, longitude, and our species data that we downloaded from GBIF, So we're assuming it's EPSG 4326, which is just like the standard spherical projection WGS 4084. So I just want to create a new data frame. In this case, is a spatial data frame called XY, which is the species input. It's just the longitude and latitude. So if you do data frame name, bracket, comma, and then everything after the comma is like, oh, okay, take those columns. In this case, take the columns longitude and latitude. Anything to the left of the comma would be selecting stuff by row. But if I don't specify a thing, it's just going to give me all the rows. So basically, I'm just saying, give me all the columns that have the name longitude, latitude. So it's 2 columns, and it's all the rows. And then I want to make sure I want to take this data frame and then convert it to a spatial data frame. So that's what this SP package SP : coordinates XY. So now I'm transforming into a spatial data frame. And then I just take those coordinates, transform it. So I now have like a whole setup where I say species location is a spatial points data frame where the coordinates are this, and the data is all the information associated with each location. And in this case, I'm forcing it so that the coordinate system that it's using is EPSG 4326. And all that's doing is I made a spatial data frame. So basically I'm telling R, like, treat this as like geographic data, kind of like how QGIS would. Now I'm going to go back and say, all right, now let's read in my shapefile for the city boundaries of LA. In this case, it's EPSG is 2229. I'm calling this object here LA boundaries. Read OGR is a command that's to read in shapefiles. Now, the whole reason I'm doing this, why I read in the coordinates here and I read in the shapefile here, is I want to take my locations, my species locations, and I want to transform them. That species location, I want to transform those species location so that's the same CRS as the LA boundaries. So in this case, it's in EPSG 2229. So this will reproject it. So now I'm going to take my lat long and I'm going to turn it to easting northing. Then what this does is take the city. When I take this, I'm going to clip my locations for all my species observations. Because right now my species observations are everything in LA County, but I want to clip to LA City. And so to do that, I take species location and only give me the ones, the spatial data that's within LA boundaries. In that case, it's bracket, LA boundaries, comma. So just the row. Just give me all the rows where the elements correspond to somewhere in LA City. So if I go back here now, I'm going to create XY. All right, so now XY is now a large matrix. Species location. Okay. And now it's a large spatial data frame. I've specified the location I'm reading in LA boundaries. Just thinking about it. Just thinking about it real hard. Okay. So I read in LA boundaries. Now we have the species locations. What I want to do is I want to reproject it. All right. Now I want to subset it so it only contains stuff within LA City. So the species location, notice here where it says like 120,000 elements. When I run it and clip it so it's only LA City, that number should drop. It's going to take a little while to run this. All right, now it dropped down to like 41,000. Okay. And now I've done all this. Now I want to convert my species locations back to a data frame. So, and the reason why is because there's a lot of other things I want to be able to do that are easier to do if I convert it back to a data frame. And now if I go and I open this, you know, it's like a third of the number of rows I had originally. Now it's only stuff in LA. It's only stuff we know down to species. And we scroll all the way over here. We have these new columns here. So notice that we have 2 more columns. And these new columns are longitude 1, latitude 1. These are now the easting northern coordinates, not the latitude longitude coordinates. And the reason why we're doing this is because the rosters we're dealing with are also going to be in easting northern coordinates. So when we're going to take these points, our species points, and put them on top of our maps to extract data, they have to be the exact same kind of coordinate structure. So that's why we want to include the easting northern coordinates. All right. And that's kind of just to get stuff set up to go from our raw input data from GBIF to, well, where is our data located in the first place in the coordinate system we want to use for this project. The next thing here is, so filter LA species observations by time and prevalence. So there's lots of different ways to do this. I just kind of went like, let's just do species locations. In this case, so by when you $, it means you're selecting a column. So if I were to just put this in the interactive terminal, it'll look like this. It just dumps everything out. So that's like every row value for the year. So it just says, all right, give me everything where the year is before 2020, after 2010, and what the species are. And the reason I'm doing this is I'm making a new data frame called species frequency. And you'll see why I'm going to do this in a second. But basically this is just an act like what I'm doing to filter out what we have so that we're only going to use species where we have at least 30 observations. So first we're going to do species frequency. I'm making a data frame here. All right. And if I open this up, what does it look like? It's literally just species name, how often it shows up. So, and the way I can actually do that is there's a command here. So if you notice here, I did species location bracket, which means, okay, take the data frame. Now we're going to subset it. So give me all the rows where the year is before 2020, after 2010. Only give me the columns where we have species. But in order to get frequency, you want to run a command called table. What table does is it allows you to say like, okay, tell me how often each value shows up in this data frame. So if I were to just run just the table command, it looks like this. This is what it looks like. It says, oh, okay, this species showed up 14 times in that data frame. This species showed up 155 times in that data frame. Okay. But now if I take that and put it in as data frame, it now takes that data and then structures it back into a spreadsheet. And again, I can post this code on the GitHub and link it to everybody so you can like actually start play around and practice this, and then edit it, see where it breaks, play around with it. Also, like ask me like, wait, why are we doing it this way? And if you have another idea how to do it, like let me know. I mean, like I said, like again, this is just kind of like a way that I've done it. All right, I'm specifying something called prevalence here, and I'm giving it a value of 30. And in this case, now I want to take my species frequency table and I want to subset it so that the frequency that I'm selecting on is greater than or equal to 30, which is what prevalence is here. So now if I look at species frequency, right now it's 2040 values. If I do that, it drops down to 293. So it's like, okay, we have like 2040 species here, but a lot of them don't show up very often. All right. Now what I want to do is rename the species frequency stuff so it's something a little more intuitive, in this case, species and frequency. And then I want to specify that species name as a character, and here is why. Because it defaults to sometimes doing it as a different data type, and sometimes it's something called a factor, which I don't want to do. But we can actually test that by doing str, which means structure. So we want to look at data types on stuff. And we can do species, frequency, species. Let's see what it thinks it is. Okay, so it thinks it's a factor with 2000 levels. So a factor is not a character. A factor is basically a variable that's kind of like an experiment. It's like an experimental type. So when you run an experiment, you have experimental groups. Each group is a factor, basically, and which is a useful data type for some stuff. But for what we're doing, we just want the names. It's not helpful. So we want to convert it to a character, which just means a string. It's just like literally a name. So that's why I'm doing this. I'm specifying it. So as character. So now when I rerun this, now it thinks that, okay, CHR means character. All right. So now it knows it's a character. Great. Anyway, I don't know if like, do people want me to keep going through on this, or do you have any questions you want me to stop, or? I don't know. Okay, let's see. Kind of random, but for loading packages, do you know if there's a difference between require and library? Yeah, there is a difference. It's something really arcane. You can use either, it's fine. I know, like, it's one of these like weird things. I've looked it up before, and I cannot for the life of me remember what exactly the difference was. I just got in the habit of using require. They should both work. I think if you Google like R difference between library and require, you'll get some answer. But I remember reading it, and it was just like, I don't know. It was like one of these things where like I'm not sure if it really matters. For whatever reason, on the remote machines I use, require tends to work more often. That's why I got in the habit of doing it. I'm sure there's some really deep computer science reason for this. I don't know what it is. All right. Anyway, this is, by the way,
I think you're sitting on your mic or something. We
Oh,
can't hear you.
wait, hello? Can you hear me now?
Now we can, yeah.
Oh. Okay. I don't actually know where the mic is on my laptop, technically. So, okay. What I was saying is like, we're just doing, oh, okay. So what we're doing is we're organizing data at this point. We're not anywhere at the point of running a machine learning model. We're just taking all of our data to get ready to throw into the model. So far, all we've done, like what we've done is we've made sure, okay, only get the species observations in LA City, and only get the ones that are recorded at least 30 times. So, do you want me to go any further in the code, or?
It was definitely interesting to see. I'm not sure like how much would help me going further in depth, because I'm like, yeah, pretty much it all looks pretty new to me, even like the very basic steps.
Oh, don't worry about that.
Yeah, no. It's good to see it. I think I'll get more experience coming in spring.
One of the things too, and as like I said, I can share this, is honestly, it's kind of like how I learned web design, is I just looked at the view source on page and played with it just to see where things would break, or just what happens when you run it. What do error messages, like basically, and then copy pasting error messages into Google. So like my goal with this, just if you can learn, if like whatever you can learn with coding is great, but like don't stress about like how far you necessarily get with it. And I do want you all to just stop me or just like ask me whatever question comes to mind. I've been coding for 20 years. It's the only reason, like, it's just sort of some of the stuff is like become kind of like I just do, but it's like mostly just because I've been doing it for a really long time. That's all. But I do remember like being in high school, like staring at this stuff and like, what is this? 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 Oh, the commands are not on GitHub yet. This is a really good question. What I can do is the code that we're going over, I can just copy and paste what we've gone over so far into GitHub, and then I'll send everybody the link. That's kind of what I'm planning on doing. So I don't know if you want to just kind of take a break here or you want me to keep going. Listen, either way. So. Break. Okay. Do you want to just like, well, yeah, you're gonna have to talk to me for a bit longer anyway. My throat is dry. Okay. So what I'm doing, I'm gonna stop this. I'm gonna upload the video. We'll regroup at 4. Is that okay? All right. You're doing great. All right. I appreciate this. I know it's a lot. So all right. I'm gonna stop share right now. Stop recording.